Swayam Prabha. Digital India. Educated India.
Then welcome to lecture number 6 of this Gaian course in high fidelity lattice Boltzmann methods. And today we are talking about implicit collision operators. And this is now a little bit less fancy than it sounds, because what I want to imply by this is not that I invent some strange new implicit collision operator. Rather, I want to convince you that the collision operators that are usually used in lattice Boltzmann, that they are implicit. And this is the reason why the lattice Boltzmann method works in the first place. Because if you are going to use lattice Boltzmann and you run into people who are dealing with numerical fluid dynamics or other things, or even with the Boltzmann equation, you will usually be confronted with the question, why are you doing this? I mean, you have the Navier-Stokes equation, you have fluents, ANSYS, whatever, yeah, so you can solve we know how to solve the Navier-Stokes equation. If you want to solve the Navier-Stokes equation, why don't you go ahead and solve the Navier-Stokes equation? So in general, you will be challenged by the question whether it's a good idea to use kinetic methods to solve the Navier-Stokes equation. And I can tell you, the people who are quickest in asking these questions are the people who are actually who are actually working on kinetic methods. They kind of have the impression that you are something dirty when you use the lattice Boltzmann method. You are trampling on their theory. Yeah, so they want to do a discontinuous flow, whatever, and now you come and solve it. We just want to solve the Navier-Stokes equation. Isn't this easy? Aren't there more easy ways to do this? So, what is the most important reason why you should not use a kinetic method to solve the Navier-Stokes equation? The reason here is that you need to resolve the particles collisions. So you have to resolve particle collisions. This means that you have to resolve mean-free time and potentially mean-free space. So the mean-free path in air, as we said, is of course depending on pressure. On your big mountains here in India, it will be like almost 4 times longer than down here at sea level. Yeah, but here at sea level, it will be of the order of 60 nanometers or 100 nanometers. You have a speed of sound of, I would say, roughly 340 meters per second. And this means you have a mean free time, which is proportional to the mean free path divided by the velocity of 0.17. Yeah, so it doesn't really matter, say 0.1, 0.2 nanoseconds. Now the big question we have to ask is, do we need to resolve this? Well, in a way, yes. So kinetic methods, if you want to capture kinetic kinetic effects, they have to resolve this. Yeah, so this is the time scale at which, you know, the kinetic equation evolves. Now let us look at the BGK operator, collision operator. Now specifically for LBM. So we are using the sometimes it's called LBGK, yeah? Lattice BGK, yeah, equation. So now we have this thing here that we call our, I mean, my nomenclature is not always 100% consistent, because this omega, we like to call this the collision operator. Actually, from a mathematical point of view, it's not really an operator. So this is what you have to add to so it's the change in the distribution function due to collision, yeah? So it's an additive thing, so it's not really an operator because it's not multiplied with the collision. But anyway, we often call this collision operator. So this is the change, so it's the post-collision state minus the pre-collision state. So this means it's the change. And this is given as omega into F equilibrium minus the pre-collision state. And this is obviously an explicit algorithm. So why is it explicit? So the thing that we want to know is the after collision part, yeah? So usually this is written down a little bit different. So we put this Fi on the right hand side, because we know everything that we know we put on the right hand side. And in fact, everything that we have done on the right hand side is stuff that we know. Yeah? So we know the pre-collision state. From the pre-collision state, we can compute the conserved quantities. From the conserved quantities, we compute the equilibrium. So we know everything on the right hand side. So this is an explicit method. Yeah? So we just put it in, get the result. No iteration, right? However, as we have discussed, we are not solving the Boltzmann equation for either F or F star, but we solve the Boltzmann equation, or the reduced Boltzmann equation for the average of the two, yeah, namely F, what we call here F over bar, F, and this is Fi plus Fi star 1/2, and this can be written also like this, because I mean I want to replace this, so I have to rewrite this as Fi half minus Fi asterisk half plus Fi bar, and now I can plug this into this position here to see that I get Fi, so the collision here is omega Fi eq minus Fi over bar minus Fi minus Fi star divided by 1/2. Then I bring this here to the other side, so I now this is now implicit, right? So here we have Fi star on the right hand side. So we bring this to the other side, as we have already done when we derived the Navier-Stokes equation. So I'm just repeating this, or I'm just giving the result for this. This turns out to be 1 over omega minus 1/2 Fi equilibrium minus Fi over bar. Now this still is implicit because inside Fi over bar is the outcome, right? So now this is implicit for the thing we are actually solving for. Okay, so what we discover is that our algorithm is explicit for Fi, but we are not actually solving for Fi, we are solving for Fi over bar. And for Fi over bar, this algorithm is implicit. Yeah? So, but this is something that we never use, so the algorithm is explicit, but the method is still implicit. You have to wrap your brain around this a little bit. What is the consequence of this? The consequence of this is that this method now behaves like an implicit integrator for the collision time. So usually, if we have this physical effect or the collisions, we would have to resolve the collisions. Meaning that the time step of our method has to be shorter than the mean free time, than tau. Otherwise, we cannot do this integration if we have an explicit algorithm. Now, if you have an implicit algorithm, you know that implicit algorithms don't have a time constraint. Yeah? So they can have arbitrary long time steps. So we actually have no stability limit of this. We have no stability limit on the collision time. I mean, this does not mean that we don't have a stability limit. We come to our stability limit later. And the thing now is that our tau can be described as 1 over omega minus 1/2 into delta t. Or otherwise, we can say that our implicit, I will remove this here later, but omega implicit is basically delta t divided by tau plus 1/2 delta t. In our implicit BGK. Now, there are actually, okay, the history of this is rather funny, because what I have observed in the 25-ish years that I do lattice Boltzmann now is that often mathematicians saw this primitive method that we are using and thought that, okay, so they are using Euler forward with some strange tricks. We know better. We can discretize this in a better way. So and then they would discretize the lattice Boltzmann equation in their mind properly, and then what they have is they would actually get the so to speak correct omega, and the correct omega would have to be delta t by tau. Yeah, so this would be an actual in an explicit scheme where you already, where you don't have this strange change of variables that we are using. Yeah. So now, how do these things compare? Yeah, you can easily see that. So this you could say is the physically correct collision frequency. Yeah. So if you have to resolve the collision frequency and you do you do your Boltzmann equation, your BGK equation with this, and your tau is much, much smaller than delta x. You see that this guy here gets very, very large. And so you multiply this non-equilibrium part by a very, very large value. And you can imagine this is going to be, could be difficult. So in particular, if delta t is very much larger than tau, what you would like to have, because you remember 0.1 nanoseconds, 0.2 nanoseconds, yeah? So this implies for the implicit method, which we are using, that omega would go to 2, whereas for anything that you can term to be correct, it would mean that omega would have to go to infinity, which you can imagine does not work very well if you try to do it. So if we just look what happens to this operator or this operation, for omega equal to 2, yeah, so we had this in the discussion already a little bit. So omega equal to 2 means no viscosity. And I mean, I've already told you what this is, but now we can plug it in and see. So you get the post-collision is twice now the equilibrium minus once the pre-collision. So one thing that you notice is that everything that you do operations here are of similar size, right? Because usually F should not be much different from F equilibrium. Yeah? So then the numbers you are dealing with, they are all of similar size, and this is what we call well-conditioned computation. So whereas you can imagine if you have to instead multiply this by infinity, this is definitely not a well-conditioned operation. Yeah, so you would add up numbers of very different sizes. Another thing, okay, so another thing that you observe here, I don't have this in my notes, but you would see that in this case, Fi is also 2Fi equilibrium minus Fi asterisk, right? So this is what we had discussed yesterday or the day before, I don't remember. So you see that if you are at omega equal to 2, your system goes forward as it goes backward. So you lose the arrow of time. Omega equal to 2 here in this case, yeah, or tau equals to 0 would mean you don't have an arrow of time. So this is what at the end of the 19th century or the beginning 20th century the physicists started to understand. Yeah, so in Einstein's paper basically, that because you have an arrow of time, means that the matter cannot be discontinuous. So there must be a smallest scale. The smallest scale is the thing that actually gives us time. Yeah? Strange how things are connected. Okay, now okay, now we understand that we cannot put things the omega to 2, but we can put it larger than 1. And this regime between omega larger than 1, omega 2 larger than omega and omega larger than 1, this regime is called over-relaxation. Over-relaxation. And there's actually another funny thing, another funny history. Oops, what's that? What did I do? Another funny history is that there is a US patent on over-relaxation in lattice Boltzmann. The scientific world never bothered, and this is somewhere in the around the year 1990. So I think it's past, yeah, it's past its value. But these company that is selling this, the company EXA that developed the power flow algorithm, that is a power flow software, which is a lattice Boltzmann software used in the automotive industry since roughly 1990, mostly to, so I mean, like for 25 years, all automobiles, so all cars in the market have been calculated with lattice Boltzmann. I think this is something that many people do not really appreciate. Yeah, lattice Boltzmann is there for a very long time. Yeah, and nowadays there's a lot of other software, open form, and so, and the cars nowadays use actually less lattice Boltzmann than in the 90s and in the early 2000s, where power flow was the only software that was available to do this kind of calculations. So lattice Boltzmann, yeah, it has played a major role in the shaping cars over a few decades from roughly 1990 into the 2000s. So, and they have this patent on over-relaxation. Now it's over-relaxation is extremely important. This can only be done with implicit collision operators, and it is the only reason why lattice Boltzmann has survived in this world in the first place. So let me try to draw a picture. Suppose we draw our state space, yeah, the state space of F, yeah, this is composed of different moments, and usually it's composed of many moments, so it's a very high-dimensional space, yeah. Since I cannot draw a high-dimensional space, I pretend now that this is made up of just two moments, M1 and M2, yeah. So, and in this space, so there are a few points, namely the F equilibrium, so that's the equilibrium point. And now you could do something which I'm never good at, is drawing a circle. Drawing a circle around this and saying the following. So, okay, now we need something else. We also need this point, and this point is the incoming distribution. So say this is the the distribution that we have at the start of a collision, yeah, and this is the corresponding equilibrium distribution to this state, yeah. So then we have, so what's, okay, so then everything within this sphere, yeah, because it will be a sphere in many dimensions, everything within the sphere is closer to the equilibrium than F. And everything on the sphere is as close to the equilibrium as F. right? So if we define time in the way that we go towards the equilibrium, what we have to do is we have to find a point inside this sphere, yeah, that will be the outcome of the simulation. Now, you see already that we would have a lot of opportunities here because we can treat the different moments in different ways. Yeah, so we could basically go, for example, here. Yeah. So, but in the BGK operator, we say we don't yet know how moments work. So we make a following decision that is completely independent of how we define our moments. Yeah, we say we take the point, so to speak, we take the point exactly opposite, yeah, to this, and this is, and now we interpolate between these two things, or we could, okay. So this is one interpretation, or the other interpretation is that this omega, so we have the distance. So I mean, this line here is obviously the distance of the equilibrium and the distribution, and the omega is the distance, the part of this, the fraction of this distance that we are using to compute our post-collision state, right? So, and now when omega is smaller than 1, we end up on this side, obviously, right? But when omega is larger than 1, we would end up on this side. Yeah? So you see, meaning saying that we go toward equilibrium does not mean that we stay on the current side of the equilibrium. We can get closer to the equilibrium, but we can overshoot. Yeah? So, and when we overshoot to this, actually, one thing that you always have to keep in mind, because this is now F asterisk, yeah? So, I mean, how do you get to, one understanding, how do you get directly to equilibrium? Omega equal to 2, right? But this you know only because you already know that this is an implicit operator and that we are solving for F over bar. Because if you thought otherwise, what you would say is, oh, I want to go directly to equilibrium, I put omega equal to 1, that my post-collision state would be here. Yeah? However, what you need to know and what you have learned in this course is that actually the thing we are solving for is the average between the two. So, and when this is, so say, when this here is the incoming distribution and you want to be here, then you would have to have the outgoing distribution there, yeah, such that their average is directly in the equilibrium, right? And actually, this would be the only point that gives you F over bar in equilibrium, right? So, so because we have this contraction here, so we are getting closer, even if we overshoot, this means we have a linear stability. For omega being in 0, so including 0 and excluding 2. Then we will be stable. So this here, this blue one, is under relaxation, and the green one is over relaxation. So if you do under relaxation, you resolve the time scale of the collision. Yeah, so you have a time step that is shorter than the collision time. Yeah. No, it's not. Okay, we have to, in order to be precise, the collision time is the time that the collision takes place. What we mean is the time between collisions. Yeah. So the time. This is the important thing. You would be short. The time step would be shorter than the time between collisions. If you do over relaxation, your time step is longer than the time between collisions. And the amazing thing is that this works, and that this actually gets pretty close to an infinite time step because we have an implicit collision operator. So does this mean that we are unconditionally stable? Unfortunately, this is not the case because we have something else. We have something else to deal with. Yes, please use the microphone.
Where we will land if omega equal to 2 in that circle or outside
If
the
omega
circle?
is equal to 2, we will land here. We will land exactly on the opposite. Okay, I'm not drawn it properly. So, who is the antipode of Chennai? So when we are in Germany, we always say if you dug a hole through the earth, we'll end up in New Zealand. So where are you going here? It will be something in the Pacific. No, somewhere in the Pacific. Or do we get to Chile? I don't know. Maybe you end up in Chile, right? So you go exactly to the opposite side of this sphere. So, okay, we don't have. Yeah.
So in the under relaxation case also, is this stable?
Yes, the under relaxation case is stable, but being stable does not necessarily mean it is accurate. Okay, there you have a different problem. Because we are doing Lattice-Boltzmann and we have done our discretization basically for solving the Navier-Stokes equation. Yeah, so if you were hoping that doing under relaxation you suddenly get more kinetic effects, then unfortunately not. Yeah, because we cut off this. We have used too few speeds, right? So then actually, if you do too much under relaxation, you may lose your connection to the Navier-Stokes equation, and you get something that is called lattice artifact. So you'll see more and more of the anisotropy of your discretization. So usually, Lattice-Boltzmann is used in over-relaxation mode. You can do a little bit under relaxation, but you cannot heavily under-relax. Okay, so let's come to the stability. So of course we still have stability bound, but the stability bound does not come from the collision. That does not, but from the streaming. Because streaming, what do I write? Because streaming is also an explicit algorithm, and there we have to deal with the CFL condition. So who of you never heard about the CFL condition? Who of you have heard about the CFL condition? So there are very few people who have neither heard nor not heard. Yeah, it's they're in some quantum state, right? Okay, so most of you have heard about the CFL condition. This is Kurov, Friedrichs, and Levy in, I think, pretty much accurately I think it's 1924 or 27, I don't know, roughly 100 years ago. Yeah, just stating that information cannot move faster than it cannot move faster in the equation. So, or when information should physically move faster, then it is allowed to move in the discretization, the method will become unstable. And this is, of course, something that we have to take care of, because we have seen we have this light cone thing here. So, and now there are three different modes by which information is carried on in the lattice-Boltzmann method. The first one is the advection. And this is pretty much the same to an explicit Navier-Stokes solver. Yeah, you have a velocity u that is carrying stuff around. Yeah, so then there is, in addition, because this is not properly incompressible, there's also a sound wave. Sound. So this is CS, the speed of sound. Now there is one important thing here to notice, namely that if the fluid is moving around, so then it will also carry the sound waves. Yeah, basically, so this is called the Doppler effect. Yeah, fluid is moving, so then the sound wave goes faster in the direction it is moving than where it's coming from. This is why these things add up. So you have to add the speed of sound. So it's not either the speed of sound or the speed or the advection, but it's the sum of the two. And then there is something that we usually drop because it is of very low concern in most cases. And this is that things can also move due to diffusion. But in principle, we would also have to add this here. And I have to admit, that I'm making an educated guess how this looks like. There could actually be a factor in front of this. Yeah, but it would be something like the square root of the viscosity times the derivative of the velocity. Do you agree that there should be something like the so-called diffusive CFL condition? Yeah. So this is advection. This is acoustic, and there is diffusion. And these things add up. Yeah. These things add up, and all together they need to be smaller than delta x by delta t, because this is the velocity at which information flows on the lattice. So this is the final stability criterion for the lattice-Boltzmann method. So your method will crash when you violate this condition. And by the way, now we have a chicken and egg problem, because whenever it crashes, it will violate this condition. It is almost impossible that it crashes without violating this condition. So does it crash because it violates this condition, or does it violate the condition because it crashes? That's a difficult question, but your program crashes once this barrier is hit. Yeah, so this is the end of your simulation. So this means for your time step that it has to be smaller than delta x divided by the magnitude of u plus cs plus this thing that is some derivative of u, yeah, and times the viscosity. Yeah. So don't nail me down on this. There may be a factor of order 1 in front of this. Okay. So usually we don't care about this, because this thing is usually so small compared to the others that we are that we have the tendency to ignore this. I'll also do this now. So, for example, delta x, we say our delta x would be 1 millimeter, and just assuming we ignore velocity, then our delta t would be 3 by the, and delta t is smaller than 3 by the power of minus 6 seconds. Yeah, so due to the physically correct speed of sound of 340 something meters per second, what you can do is you can use a different speed of sound. This is often done. If you run your simulation with an incorrect Mach number, you can often increase your time step because the CFL condition becomes less severe. Yeah. So, yeah. Okay. Important thing to remember is LBM is only with us nowadays because it's efficient, and it's only efficient because it uses over-relaxation. So I told you I've been, yeah.
So in this case, how will we choose the delta x and delta t? They need to be same, right?
How do we choose the delta x and delta t? Okay, so we choose. Okay, so you choose the delta x by how you think here. So usually you choose your delta x by the thickness of the boundary layer that you expect, for example. Yeah. And then if you, so then depends on your problem. So suppose you have an acoustic problem, yeah, and you want to, okay, yeah, so how would you do it? So delta x is given by, say, your problem, yeah, so, I mean, everything is given by your problem, yeah, but by the resolution, you assume that is necessary to resolve your boundary layer, for example. Then you have to make a choice whether you use the correct speed of sound or you have a scaled speed of sound. But say you believe in physics and we want to have the right speed of sound, then this speed of sound should now correspond to, I mean, okay, so let's put it that way. I notice I'm probably speaking nonsense here, because if you have decided on delta x and you'll decide on using a specific speed of sound, then obviously you have already fixed delta t. So then there is no other choice than delta t, because you know that 340 meters or 344 meters per second is then equal to square root 1/3 delta x by delta t. So then for a given delta t, you would have a fixed, or for a given delta x, will have a fixed delta t. Yeah. However, you don't need to use this 340 meters per second as a speed of sound. You could also choose a lower speed of sound, yeah, so to manipulate your time step. However, this goes only as far as you can handle this within this context here, such that the velocity that you are looking at, if you add your velocity, so the highest velocity that you would have in your system, and you have to remember in turbulent flow, the highest velocity is not necessarily the one that is in the input. We can have higher velocities inside than on the boundaries because we have not a linear system. Yeah. So the highest velocity that you could expect plus the speed of sound have to be chosen. So they give you the smallest times, the largest time step that would remain stable. Yeah. Okay.
Sir, but in LBM, we have a condition that the time step and the grid spacing are interlinked. Delta
Yeah.
x and delta t is equals to 1. But here we have chosen delta x to be 1.
Then okay. So
But
okay. So we need to express all the quantities in letters Boltzmann in terms of delta x and delta t. Yeah. So this means that in the numerics, when we put the velocity, yeah, we always have the units delta x and delta t equal to 1. So we multiply them by 1 so that we get the correct numbers for computing our equilibrium function. So this is what the algorithm does. But this doesn't mean that delta x is physically 1 and delta t is physically 1, because this doesn't make sense. Delta x must be something in meter and delta t must be something in seconds. Right? So you need a scaling. Now there are two worlds. There is the physical world where your interpretation goes, and there is the numerical world where your algorithm works. And in this numerical world, everything has to be expressed in delta x and delta t. So therefore we set this to 1 in the algorithm. Yeah? Now, when you map your simulation result to the real world, then you have to decide what is delta x and what is delta t. Yeah? So this delta t in this, so here if you enter, so this is the idea. If you enter u in meters per second, cs in meters per second, and delta x in meters per second, then you get the largest time step in seconds that you can afford. Yeah, so everything now is units. Yeah. Okay, I was going to tell the story that I went to a lot of conferences on lattice Boltzmann, and there were often young PhD students from the mathematics department that, as I previously said, found a way to make a real explicit collision operator that does not need over-relaxation and actually did not work with over-relaxation. So they always showed this finite element discretization of the lattice Boltzmann equation, blah, blah, blah. And you would see this PhD students, and probably they made a PhD in another topic then later, but you would see these guys only once in your life. Yeah? And then unfortunately they hadn't written their paper because next year would be a new PhD student inventing exactly the same method again, being very proud until they discovered that they have absolutely prohibitively small time steps in their finite element discretization of the Boltzmann equation because they could not use over-relaxation. Yeah? And then everything crazy. So they simply didn't get an efficient algorithm. So lattice Boltzmann is efficient because there is this Heon correction that was originally perceived as being an error. Yeah? So there is an error. What Heon discovered, yeah, there is this error, but this error is a constant. We just subtract it, and then the error is gone. Yeah, so this was his simple solution. Now we know this is actually because the collision operator is really implicit. Yeah. So Whether you care about this or just find it works and everything is fine, yeah, doesn't matter. The thing is, we do over relaxation. We can do over relaxation, and due to over relaxation, our method is efficient. I mean, whether it is more efficient than the Navier-Stokes equation, this is a different question, because in essence, we have the same time step restriction like an explicit Lattice-Boltzmann method. Explicit Navier-Stokes solver. Sorry. So another thing is a little bit unfortunate. There is no kinetic physics left. Yeah, I mean this is what we actually left out by choosing only few speeds. And in particular, if we have this delta t is much larger than tau. Also, Newton's number square is going to 0. Yeah. So with this, we have eliminated the kinetics in our kinetic solver. Yeah. We are now solving only the Navier-Stokes equation, but we solved the Navier-Stokes equation with roughly the same efficiency as a Navier-Stokes solver would solve. No, okay, I'm not an advertisement guy. Yeah, I cannot tell you why you should absolutely use the Lattice-Boltzmann for solving the Navier-Stokes equation, because these are similar things. So we often speak about a conservation law of complexity. Yeah. So basically, you can come from the Navier-Stokes equation, build an efficient solver. You can come from the Boltzmann equation, build an efficient solver, and they would, so both of them, if you really go to the edge of what can be done, then actually they are pretty similar. Yeah, it's like you go to a race in the Olympics. Yeah, so the people running there, they are pretty close together. Yeah. So there is one kinetic legacy in our model that's quite interesting and distinguish it from most Navier-Stokes solver, and this is the linear advection operator. So this can be sometimes useful. Yeah. So in Navier-Stokes we have a nonlinear advection operator. Here we have a linear advection operator. Okay, let's look at our discrete equilibrium function. This is a little bit the thing that we had in the exercise yesterday. So now actually I'm getting a little bit repetitive to what we already had yesterday in the hands-on sessions. Yeah, so our two-dimensional code would use things like this. So we have these populations with the Miller indices that come from crystallography. This is -1, -1. f 1, 1, f minus 1, minus 1, f minus 1, 1, and we'll also have f 0, 0, right? So this is our d2q9 velocity set. So we'll always use the number of dimensions first, d2 in 2 dimensions, and now it has 9 quantum numbers, as we say, so 9 different speeds. So here's 9 different velocities. So about the discrete equilibrium functions, there are basically 3 common methods. You have a question? Please use the microphone.
The advection equation in the Lattice-Boltzmann equation, is it
Yeah.
considering both the convection as well as the diffusion term in the Navier-Stokes equation?
Okay, can you say that again?
So we have only advection term. We don't have diffusion term in the LBM.
We have so diffusion works in a different way. The collision term. You see that when we derive the Navier-Stokes equation from the BGK equation, we get a diffusion term.
So the diffusion equation is coming from the source term, the collision operator.
The diffusion comes. Okay, good. Okay, it's interesting. The diffusion comes from the collision operator. Now this is something extremely strange because in the Navier-Stokes equation, diffusion obviously is a linear operator, right?
Yes. Yes.
Yeah, and the advection is a nonlinear operator in the Navier-Stokes equation.
Yes.
Somehow the thing has to be nonlinear, because if it was completely linear, then the problem of building quantum Lattice-Boltzmann methods, even though there was a new paper just 2 days ago, which I've not yet read, but if it was all linear, then quantum Lattice-Boltzmann would be a solved problem. Yeah, but it cannot be all linear, because you can actually prove that if it's all linear, then it doesn't cause viscosity to arise, turbulence to arise. Yeah, so there's no complexity. There's no complexity building stuff if it's completely linear. So how comes? It's very strange. The diffusion in the Lattice-Boltzmann method and in the Boltzmann equation itself is nonlinear, whereas the advection is linear. Now you derive the Navier-Stokes equation, and what comes out that the diffusion is linear and the advection is nonlinear. Please explain how this came to be. I don't know, but this is the result. Yeah. So Boltzmann equation, diffusion nonlinear, advection linear. Navier-Stokes equation, advection nonlinear, diffusion linear. It's the outcome of.
And one more question is, so this Lattice-Boltzmann method, the idea is to advect these particles.
Advect, in what sense advect?
Like you stream, you collide.
Yeah, but this is not advection. Advection is when the macroscopic arising velocity field is transporting something. That's advection.
Okay, so we have a collision operator, we have collision, we have advection or streaming operation.
Yes, we have streaming, yeah.
So let's assume that if I want to solve just a diffusion equation where there is no convection term.
Yeah.
Okay, so in that case, should I drop out this the linear term that we have in the BGK?
No, you would drop out.
Which term should I drop out?
So if you have, when you have no velocity.
Yes, no velocity. I'm just solving.
Okay, so when you have no
equation.
velocity, then you simply set all the velocities to 0. And then obviously the nonlinear part, that's linear. So a pure diffusion problem, so if you solve a pure diffusion problem, then the equilibrium function is a linear function of whatever density you want to, quantity you want to, transport, and then the entire method is linear. Yes.
So if I just set the velocity is equal to 0, will it be numerically stable, or
Yeah, when you
will the
put the
solution
velocity to
converge,
0,
or
it is
will...
numerical stable. Yeah. I mean, you still have to fulfill the diffusive CFL condition. That means
yes.
the diffusivity must not be too high.
Okay, thank you.
Yeah. Okay. Let's move on to the three different common ways to compute the equilibrium function. Yeah. So, and the first one is the one that we had also yesterday, is the moment matching. So moment matching, reminding you, moments, MAB. So again, this is now getting a little bit repetitive. So we'll start from -1, not from 1. And going to 1 for I and j, I by the power of A and j by the power of B, Fij, and in this, running out of digital ink. I don't know why this always happens. So M, the conserved moments, is always the same as the conserved moments equilibrium. Forget it. M00 is density or mass, the way you interpret it. M10 is equal to rho u. M01 is equal to to rho v. And then we have M20 equilibrium, of course. Who succeeded in deriving the equilibrium populations of you yesterday? Give me hands. Nobody? So okay, one or two people were able to derive it. So we'll have to practice a little bit before we do our hackathon. M20. So what was this? This was rho times the speed of sound square plus u square. And then we had M02 equilibrium rho cs square plus u square plus v square. Plus v square. And now we have the mixed moments, M11 equilibrium, and there we have learned that this is M10 times M. Okay, I'm not good at saying what I'm writing. Yeah, very sorry for this. So this is this here, and this is rho times u times v. And now you also get all the others, like M12 equilibrium is equal to M10, M02 equilibrium. So I don't write equilibrium here because this is the same as its equilibrium. M00 is equal to rho u cs square plus v square. Then M21 equilibrium is M20 equilibrium times M01 divided by M00. Obviously, this gives us rho v cs square plus u square. which one is missing? Missing is M22 is equal to M20 times M02 divided by M00 is then equal to rho. So what do we have? Rho CS square plus U square times CS square plus V square. Was this what you? No. M20 dot plus. Yes. Thank you. Okay, so these are all these moments, and now what you would have to do is to solve them for the populations. By the way, I don't know whether this has become clear. So when we talk about all the f's, yeah, all the f's together, this is the distribution. When we talk about one individual f, this is a population. Yeah, so this is the distribution is the populations, if you will. Yeah. So this is the moment matching equilibrium. And in this, we observe that that we have some third order in velocity terms, or that actually some third order in velocity terms are missing. So we'll not have any u cube, yeah? So we have u squared times v, and we have v squared times u, but we don't have u cube, yeah, in this. But we have terms of higher order, u square, v square. This is present. And therefore, this equilibrium is actually anisotropic. This is an anisotropic equilibrium. So there is another. There's some people complain about this. Not completely clear what this means, but this is just a fact. Then there is another possibility. Somebody of you addressed this yesterday after we had this exercise. Why don't we use Taylor expansion of the Maxwell-Boltzmann? Of the Maxwell-Boltzmann equilibrium. So, and this we would usually do to second order. Second order in velocity.
Sir.
Yes?
Sir, what is anisotropic?
Anisotropic is if something does not, something is anisotropic if it does not behave in all directions in the same way.
That is anisotropic, right?
Hmm?
What do you mean by anisotropic equilibrium?
Yeah, I mean by an anisotropic equilibrium is that it is not invariant under rotation around any of its axes.
So when it will be isotropic equilibrium in this case?
The Maxwell, so the Taylor expansion equilibrium is isotropic. So you can turn you can rotate your coordinate system and the same equilibrium turns out.
No, I have that picture, but let's assume that I have a u cube v square.
Yeah.
In that case, is it anisotropic?
U2.
U cube v square.
So in what sense do we have this?
No, so you just wrote u square v square is present. That's why it's anisotropic equilibrium.
Yeah, so it's, see, when we rotate a polynomial, I mean it's not like you have, okay, it is a bit more complicated. It's a bit more complicated than said that you just have all the different terms and then it's isotropic. If you have infinitely many terms, it is isotropic, but otherwise it may not actually be all isotropic. I mean, so basically it will be like this, that you have a polynomial with u square v, and you rotate this along one axis or the perpendicular axis, or in that plane, yeah, to another position, then this u square v would partially map onto in the new version to the u cube, yeah, or u dash cube, right? So then this rotated equilibrium, this rotated polynomial would not fit on the previous one, yeah. So, but I cannot tell you now. This I would have to research and try out myself how this works with when you take many terms. The one thing I can tell you is that you take a polynomial of second order, where you have all the second order terms. So where you have u square, v square, and u times v. If you have all these things, yeah, then you can rotate this polynomial, and it will end up being again the same polynomial. I mean, the coefficients would be different, but it would have the same terms. So the advantage of doing a second order Taylor expansion of, say, the Maxwell-Boltzmann distribution, which itself is isotropic, obviously, because it has infinitely many terms. The advantage of this is that this is isotropic. Now, what we have not discussed is what is actually the advantage of being isotropic versus not being isotropic. Yeah? So this is, we sometimes state something as an end in itself. Yeah? So, I mean, being isotropic obviously has the advantage that nature is isotropic, and you want your simulation to be isotropic. So if you hear that your equilibrium is isotropic, then you are happy because you think this is the step in the right direction, having this being isotropic. Problem being that your method is not necessarily isotropic only because your equilibrium is isotropic. There's more to it than just the equilibrium. But the equilibrium would be isotropic, and the moment matching equilibrium is actually non-isotropic. I tell you this because I will tell you later that you always should use a moment matching equilibrium. Yeah? because this is in reality is moment matching equilibrium so much better when it just has this one disadvantage, that it's not isotropic. Yes, in velocity. So, okay, how does this look like? I thought we had a little bit, okay. I'm taking, again, a little bit over time, I believe, today. FIEQ comes with a weight function, Fi. So now this has only one index here, because this is the way this is usually written down. And we have E, so this is the direction vector. That is the direction of this particular link or population times the velocity divided by cs square plus ei times u square. So you notice that this is not, again, this is not consistent with its units, because we have already taken these units out. Here's 2 cs square. So I hope that this is the correct equilibrium, because I did not compute it myself. I just take this from Wikipedia. Yeah. So because you see, I'm not using this one, I would encourage you to use moment matching equilibrium. But this is the one that you will find on Wikipedia. Yeah. So I was asked, what are the books for this course? Yeah, you know, we try to be a little bit different from the books here. This is because we want to go a step further. So this Wi, these are the weights that can be obtained at velocity 0 and rho equal to 1. From the Boltzmann equation, so this Wi depend on the direction in the lattice. So this guy here is now, as I was just trying to explain, this is isotropic, but is missing higher order terms. That it is missing higher order terms has consequences. In particular, so the consequence of this being isotropic and non-isotropic is in particular the following. You will see that the viscosity of this algorithm of this thing here is dependent on velocity, which is an error. Yeah. So of course, models always have errors, and one of the errors is that the viscosity is dependent on velocity, which it should not. The advantage of this algorithm, of this equilibrium distribution here, is that this error in viscosity is isotropic, so it does not depend on direction. If you use the moment matching equilibrium, because this is not isotropic, the error will then depend on the direction. However, because there are the other equilibrium is actually better, so it contains more terms, the error is much smaller. And it's actually like this, that the error is in all directions that you can have smaller if you use the moment matching methods than it is everywhere with the Taylor expanded. Yeah. So now you have to decide on yourself what you want. Do you want an error that is small but dependent on direction, or you want to have an error that is large but independent of direction. Yeah? This is a matter of taste, and different people have come to different conclusions. Okay? So, that's the... and okay, so there is one, other than that, there is one important thing that people can understand better, namely that this Taylor expanded equilibrium is substantially less stable. So the method that if you run it with this, it will be substantially less stable than if you use moment matching. This is the best reason why you should use moment matching. Okay, so then there is, as a third part, there is an entropic equilibrium. It's actually promoted by the bunker. You have a question, yeah?
In the Taylor expansion case, can't we expand it to up to the higher order, third order?
Yes.
It will contain all the
okay.
terms.
We can expand it to a higher order. The problem then is it will no longer fit on that lattice. Yeah. So basically, or you could do something else. You could obtain. I mean, in principle, the methods are compatible. Yeah. So you can Taylor expand this to an arbitrary order, and then drop out the terms that do not fit on your discretization, which then you have to do by hand, yeah? And then you end up with the same equilibrium that you also got from moment matching. So in principle, they are compatible, yeah? But we do the moment matching because when we have already decided what moments we have. Of course, this is the prerequisite, that we know what moments we have and we match these moments. And then we already know where we have to, what terms we take into account. If you do the Taylor expansion, you need to know somehow where to truncate your Taylor expansion, yeah? Which you can determine by thinking hard, yeah? But here we already know. So in principle, these two things are completely compatible. The one thing that is not compatible with this is the entropic equilibrium. Anybody here from Bangalore? No, you. Okay, so in Bangalore they promote this entropic letters. Do you use this? Okay, so I don't know whether they are from mechanical background, but anyway. So in Bangalore, they promoting this entropic equilibrium. So what is this? I have to admit that I'm not really the fan of this, but anyway. So if I try. I tell you that I'm not a fan of this because I may misrepresent it. So I try my best to represent it, and if somebody can later correct me. So we have the FIQ given with the same weights times a row, and then comes a product. I mean, I've just now we a product over alpha, and alpha are the different cardinal directions. So the x, y, and z. Yeah, if this is three-dimensional. And this is the number of dimensions is d. So this goes into 2 minus s alpha 2 u alpha. So this would be u v w if it's three-dimensional plus c s alpha divided by c minus u alpha, and this by the power of c alpha divided by c, where c is equal to delta x by delta t, and this S alpha is equal to 1 minus u divided by cs squared. So, so you can also use this equilibrium. And this, I mean, I have seen this for almost 20 years without actually understanding what the point is. Now, last year I went to a conference where somebody explained me what actually the point is, and I was wondering whether they who invented it actually knew back then what the point is, because they never pointed out what the point was. So, but now they pointed out what the point is, and now I can also point to you what this point means. So this is supposed to be more stable. You need to combine it with something else to make it really stable. But supposedly this is more stable, and the way that has now been pointed out to me why it is more stable is because it adapts the speed of sound. So it has an adaptive speed of sound. So, and since it has an adaptive speed of sound, meaning, okay, what is the meaning? If the velocity gets larger, the speed of sound gets lower. And now you look at the CFL condition and you see it's U plus CS, yeah? So, and actually when the, you see the following, when U approaches CS, then this thing here somehow gets to be 0. So this will kind of disappear. I'm still not completely sure how exactly it works, but the idea is that it adjusts the CFL condition, so your U becomes larger and larger and larger, so the speed of sound becomes smaller and smaller and smaller, yeah, such that when your speed actually gets to 1 delta x by delta t, the speed of sound would go to 0. And so you would still be stable up to a velocity of 1. Whereas the usual lattice-Boltzmann method would only be stable up to 1 minus cs square, and cs square is square root over 1/3. So basically, this adaptivity can double the CFL range, right? Because 1 over square root 3 is very, very roughly 1/2, right? So then if you withdraw this, so you can do twice this in principle at the cost of modifying the speed of sound, which I find difficult because the speed of sound is, so there are two reasons why I find this difficult. First reason is the speed of sound is, of course, a physical quantity that should stay the same. And the second thing, the speed of sound is a parameter in the viscosity. So this modification modifies your viscosity, which, you know, this is why I heard this talk, which after 20 years of using this method, these guys finally acknowledged and said, okay, if the speed of sound changes, we can on top change the omega in the opposite direction so that the viscosity stays the same, okay? I still have concerns with this because then this is, again, not isotropic, but maybe I don't see everything here, yeah? The thing is, the thing why I still find this a bit ridiculous is, first of all, we don't want to run too close to the CFL condition, also because this makes it not accurate, yeah, obviously. And the second thing is we can double the CFL condition. So there's still a CFL condition, and we can just double this, yeah? And increasing something by a factor of 2 is usually, yeah, nice, but is not really a big change, right? This is why this is why I still don't believe in this a lot. So we have adaptive speed of sound such that the CFL condition for this thing here is just U is smaller than C, and C is dx by dt. Yeah, so there's no CS in this anymore. Okay, so these were the three ways of computing equilibrium. Now we want to go to lattices in 3D, and I'm talking too slowly today, I recognize. And what we do is we start from our one-dimensional lattice with this stencil here. So this is 1D, and what we then do is we use a tensor product lattice. So tensor product means if we go to 3 dimensions, then we have Q 3 by the power of 3, and this leads us to D3Q27. So what are the countable moments of D3Q27? So there's a 0 moment, of which we have just one, namely the M00. This is once. First moments. Okay, I will not write this anymore. So we have M100, and of these we have, of course, 3 permutations, right? So second moments. So how many second moments? 6, right? So we have M200. Of these we have 3 permutations, and we have M110, of which we have 3 permutations. Then third moments. How many third moments in 3 dimensions? I have to think myself. Yeah. Give me a number. More than 2 or less than 2? I mean, more than 6 or less than 6? Okay, we have M21. How many permutations of this? I've heard 3. 6. Anyone more? I've heard 6. Okay, I have 6. Yeah, because they're all the indices are different. Yeah, so we can permutate them 6 times. But that's not all. We also have this guy, right? And this we have once. So we have 7. So forced. So what do we have on order 4? We have M220. So how many permutations of this? 3. And then we also have this guy. How many permutations? Also 3 permutations. So fifth moment. What do we have? 2, 2, 1. How many? 3.
We have a 300, the third moment.
3 in the third moment. 300. No. We don't. We are talking. Okay, the countable. Yes. So we are not talking about how many moments exist. We are talking about how many independent moments exist. Yeah. And you remember when we talked about the discrete velocity model that we don't have a moment M3, yeah, because we only have we only have 3 velocities in one direction. Yeah? Okay? So then here we have right, M, so okay, I think these have been it, and then we have this one here obviously has one permutation. So, and if you count all of them together, you'll end up with 27 independent moments. 27 independent moments. So what we need for the Navier-Stokes equation is we need the full moments, meaning the non-equilibrium plus the equilibrium moments up to the second moments. And we need the equilibrium moments for third order moment. We need the equilibrium for third order moments. So, all moments that are non-essential, we call them ghosts. Ghosts. That means we have some moments like the fourth order and the fifth order and the sixth order moments that according to our analysis don't carry any information. So why do we have them in the first place, right? And so there's two problems with this. First of all, they are waste of memory and resources because you have something that you do not need. And the other thing is the stuff that you have an organ that you don't need, right? Say you have an organ that you don't need. This organ can kill, when this organ gets sick, it can still kill you, right? So then you may want to get rid of this organ, potentially. Yeah, so it's, they are waste of memory and they are danger to stability. At least this is how they are often seen. So therefore there are attempts to get rid of them by pruning. This means you take this lattice that we had and you cut out some branches. And because this is difficult to draw, so I'm very sorry for this. But I think it's better I don't draw this and just paste it here. So the lattice that is the tensor product lattice looks like this here, the D3Q27. It's basically a cube which has velocities on the faces, on the edges, and in the corners. Now you could derive different lattice-Boltzmann methods by taking away some of the speeds. So for example, you arrive at the DQ19 method. If you leave out the corners, you can also leave in the corners and leave out the edges. And there's also a method that only have the edges and not the faces. Yeah. So this here is pretty difficult to work with actually. Yeah. So so in the beginning of the 2000s, there was a lot of thinking that you should go in this direction, less and less and less, yeah, making life simpler. And nowadays, bigger computers probably, everybody wants to go in that direction and add more and more speeds, yeah. So the biggest lattice Boltzmann stencil that I've seen has 343 speeds, yeah. Oh my God, yeah. So the modern style is adding more speeds. So as we discussed to your question, yeah, the number, so this is the number operator, the number of moments is infinite always. The number of independent moments is equal to the number of populations. So this would be 17, 19, 15, and 13. By the way, there are 10 hydrodynamic moments. It is impossible to build a lattice Boltzmann, so even it is mathematically impossible to build a lattice Boltzmann method with less than 10 moments, yeah, for the Navier-Stokes equation. 13 is the smallest that has been found. Maybe leaving the non-moving out, it would work with 12. I don't know. Yeah. So this is a small paper that you could write. See, because we need 10. Yeah. Maybe it works with 12. Then you have found yet another simplification to the world. So, because there are infinitely many moments and there's finitely many independent moments, there are obviously dependent moments. And they are, of course, fully determined by the lower order moments. So basically, the lower order moments repeat at higher order, so they have an alias, so they have a second name, and therefore we call these. So how should I pronounce aliasing? Aliasing, yeah. So because they are a product of aliasing, we call these things aliens. In reference that the others are ghosts. So the higher the moments that do not participate in the Navier-Stokes equation, they are called ghosts, and the moments that are not independent of other moments, they are called aliens. Yeah, so we distinguish this thing here. So, for example, in the lattice that we like to use, D3Q27, with our definition of moments, then MABC. So all the I, J, and K go from -1 to 1. Fij, K, I by the power of Aj by the power of K and by the power of B, sorry. By the power of B, and unfortunately I now have to use a C again, K by the power of C. So in this definition, this M220 is a ghost. M300 is equal to M100. That is an alien. And this M320 equals to okay, let's make it this one. Let's M420 is M220. This is a ghost and an alien, both together. So it can be tricky for some lattices to determine what are the independent moments. So for example, the D3Q19, which is a very common lattice. So I mean, I remember once being asked, so determining the moments for a lattice, how do you actually know? And I said, I look at the lattice and write down the moments. And then I noticed, okay, that's not a very, say, systematic way of explaining this, right? So, I mean, if you, this is, yeah, okay. So this is what Feynman said. Yeah. So look at your problem, think hard, and write down the answer. I mean, this is how it usually works. So how do we get to what are the independent moments of the D3Q19 letters, for example? So obviously, there needs to be the 10 hydrodynamic moments, M00, M100, this 3 times. Then there would be the ones, these are still hydrodynamic moments, 3 times. The second order guys, they are all present. Also this. Now you can count that this is 9. So, okay. Right, so these are the 10 hydrodynamic moments that have to be here, otherwise we cannot solve the Navier-Stokes equation. But then there are a few other guys, namely we'll have M210 6 times, and we'll have M220, we'll have this 3 times, and then, okay, this is 10 plus 9, and we are done. So how do I know that these are these moments and not other moments? Well, I showed you the picture. The D3Q19 is the one that is missing the corners. And because it's missing the corners, it does not have any degree of freedom that has all 3 components being non-zero. So this lattice will only support moments in which at least one of the indices is 0. Okay, so this is, look at it and write it down, right? So, but this is not very systematic. In fact, there is no simple way to determine this for general. What am I writing? There's no simple way to determine I'm running out of digital ink again. See, that the problem with this thing is you don't know when the battery is dead. Okay, no simple way to determine independent moments. Maybe this is the reason why it takes so long in between that new lattices are found, yeah, and there are not so many possibilities anyway. Okay, so there is of course a way how humankind has apparently done this. I mean, I always just look at it and try to figure it out somehow. But this is the way it has been done. So, how was it done? You find an arbitrary enumeration of the populations. This means not using Miller indices like we do, but only using one indices, F alpha say, and alpha being the element being in 1 to q, the number of directions that you have, the lambda of speeds that you have, with velocities C alpha x, C alpha y, and do we have to leave the building? No, okay, C alpha z. So this is the velocity. So we have a vector of the velocity for each direction. So we have an arbitrary order, but what direction we have is given by this set of velocities. Yeah, and now we can write in this way we can write our raw countable moments. So this is a way that other people like much more, me not, but maybe you are other than me and you like this more, you are welcome. So now you can compute the moment MABC as the sum over alpha of all the populations in these vectors EX alpha. So I wrote it the other way around, so I should have it alpha x by A okay, sorry, I wrote with velocities. So I wrote it C. Okay, then I write C. No, C is stupid because I use C already. So I'll use E, sorry, for this confusion. Yeah, so this is the velocities. I write them with E. Yeah, so E alpha x by the power of E alpha y by the power of B, E alpha C by the power of C. And then this can be this E alpha x, y, and z. Yeah, they can all be expressed in the. Okay, now I write it properly. So the vector E alpha x a, E alpha y b, and E alpha z c, they are expressed in vectors. Namely, in a pra vector, so pra p, a, b, and c is equal to the component 1, a, by of the. Sorry for my confusion. The alpha parameter is the first, so the first x, E1x, E1y by the power of b, and E1z. So this is going on until, so this together is by the power of c. So this together is the direction, and here we have EQx by r, EQy by b, and EQz by c. So this is how. So we multiply these vectors together, right? And this gives us this vector. And then we have, so this is a row vector, and then we have a column vector that we call a cat. This is written F. Now this is a cat, and in this cat we have F1 dot 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 until FQ. So, and now you can compute moments. This is what some people like, moments, by saying you have this vector P, A, B, and C in a scalar product on F. So this here is the moment generating vector and this is a scalar product. That people doing quantum mechanics like this, writing vectors like this with pras and cats. Now it has been done in that particular way. We check if P, A, B, and C is linearly independent of all lower order vectors So, I mean, what do we mean with lower order vectors? This means A plus A dash plus B dash plus C dash is smaller than A plus B. This is supposed to be smaller, A plus B plus C. So this is how we compare. Yeah. So if the sum of the indices is smaller, then it's the lower order. Yeah. So we take any arbitrary A, B, C, and we count all of them downwards and see whether one of the vectors that appears there or all the combinations of vectors together, yeah, this is of course important, if we are linearly independent of all these other vectors. So if we are independent, then we have an independent moment. Not independent, then we have an alien moment. So in this way, we always make sure that we keep the lowest order moments as the primary moments and the higher order ones as the ones that are the actual aliens. Okay, so this is how it has been done, and this is how I still took the 2 hours, even though I thought that I had less to talk today. There is again a change in schedule for this afternoon, but not important for you. I mean, you just have to come. We've decided that it's better to keep the exercise parts that we have planned for today and tomorrow together and do them together tomorrow. So tomorrow there will be no lecture, and the lecture that will be that was scheduled for tomorrow morning will be given today at 2 o'clock instead of the instead of the exercise, and then tomorrow morning we'll have that exercise. Okay?